we all use tools every single day to learn, to work, to, just get by.
Right.
But imagine for a second if the tools you used were actually watching you use them. Like, imagine if the hammer you bought at the hardware store noticed how you grip it. And overnight, it forged itself a better, a more ergonomic handle.
That is a wild thought. I mean, you are talking about an object that doesn't just, perform a function, but actively redesigns its own fundamental structure to perform that function better tomorrow.
Yeah, exactly. And while your physical hammer obviously isn't doing that, the software we rely on is actually starting to.
It really is.
So today, we're doing a deep dive into the absolute frontier of generative AI. We are pulling from this fascinating new paper called Hyperagents.
Right, from the researchers at Meta, the University of British Columbia, and the Vector Institute.
Yep, and we are also using insights from the text Architecting Intelligence. So the mission today is to get an inside view of how artificial intelligence is, well, moving beyond just answering our prompts.
Yeah, and to set the baseline for you, the core theme here represents a massive paradigm shift.
Definitely.
Because for the last few years, we have basically been living in the era of prompt and answer AI. You ask a question, the model gives you an answer based on its static training.
Right. It just accesses what it already knows.
Exactly. But what society is really pushing for and what these researchers are trying to unlock is self-accelerating technological progress.
And the roadblock there has always been that current AI systems, they hit a rigid ceiling.
Yes, they do. They only improve as fast as human engineers can manually tweak their underlying architecture.
So the human is the ultimate bottleneck. We are the ones typing the code to make the machine slightly smarter, which, takes months of testing.
It's incredibly slow.
But this research looks at how AI is finally breaking through that ceiling. We're transitioning toward self-improving AI that recursively makes itself smarter.
Which is huge.
But to really appreciate the breakthrough of these so-called hyperagents, we first need to understand the wall that previous models ran face first into.
Right, because prior attempts at self-improving AI were essentially trapped by their own design architecture.
Okay.
The best example of this, and this is the foundational baseline that today's research builds upon, is something called the Darwin Gödel Machine, or the DGM.
The Darwin Gödel Machine. I mean, that sounds incredibly sci-fi.
It really does, and it was a massive leap forward when it debuted because it demonstrated that open-ended self-improvement is actually achievable.
Really?
Well, at least in the narrow realm of writing code.
Ah, okay. Just code.
Right. It operated through a process of evolutionary exploration, so you start with a single coding agent.
Okay, I'm with you.
And that agent generates variations of its own source code. It is essentially proposing modifications to its own software.
Right.
And then it evaluates how well those new variants actually perform on standard coding tasks.
Okay, so it essentially builds like an evolutionary graveyard of bad code and a VIP lounge of good code, and then it only breeds the winners.
A VIP lounge is the perfect way to look at it. The DGM maintains an archive of successful variants.
Got it.
It acts as a growing library of stepping stones. So the system branches out from these successful candidates, allowing them to self-modify even further, test them again, and then adds the new winners back into the archive.
Which makes sense.
Yeah, this open-ended exploration is specifically designed to prevent the system from getting stuck in a rut.
Yeah, I mean, that sounds incredibly powerful. If it is constantly evolving and keeping the best versions of itself, what was the fatal flaw?
Well, the limitation lies entirely in the mechanism of how it decides to improve.
How so?
The DGM relies on a fixed, handcrafted, meta-level mechanism.
Okay, a fixed meta level. What does that actually mean in practice?
Think of it as a separate, isolated instruction generator that was built by a human. This mechanism looks at the AI agent's past performance, and it looks at its current code base, and then it triggers a call to a language model using a static human-written prompt.
Right.
So that prompt generates a new instruction, something like improve the error handling in this specific Python function.
Oh, I see. I think I have an analogy for this. You tell me if I am off base here.
Go for it.
It's like having an absolutely brilliant student who absorbs information and learns incredibly fast.
Right.
But they are stuck with a human teacher whose lesson plan literally hasn't changed since 1995.
Oh, exactly.
So the student get better and better at the 1995 curriculum, but the way they are being taught, like the actual pedagogical method, is entirely static.
That captures the dynamic beautifully.
Yeah.
The agent can change its coding behavior, but it absolutely cannot change the fundamental rules of how it proposes those changes.
Right.
Its capacity for self-improvement is completely bottlenecked by that 1995 lesson plan.
And if you try to fix this by say, building a software system to teach the teacher, like a meta level, you just end up in an infinite regress.
Yes, exactly.
Because you would need to build a system to teach the teacher's teacher and on forever.
You would just be pushing the human bottleneck one level higher up the chain every time. And this dynamic brings up what the researchers call the alignment problem.
The alignment problem.
Right. The original DGM was successful because evaluating code and modifying code fundamentally required the exact same skill.
Which is coding.
Right, coding. If the DGM improves its coding ability to solve a software task, it accidentally also improves its ability to write the code needed to modify itself. The skills are perfectly aligned.
But I'm guessing if you step outside of software engineering, that entirely falls apart.
Completely.
Like, let's say you want the AI to write poetry or analyze medical scans. Improving the agent's poetry writing ability does not make it better at rewriting its own Python architecture to learn faster.
Exactly. The task skill and the self-modification skill become completely decoupled at that point. Being a great poet just doesn't make you a great software engineer.
Obviously not.
Yeah.
So if the fixed teacher is the problem, the logical next step is giving the system the power to rewrite the teacher too.
Precisely.
Okay, let's unpack this, because this brings us to the core of the new research, which is the hyperagent.
Right. So a hyperagent is defined as a purely self-referential agent.
Meaning what exactly?
What the researchers did was take the task agent, that's the part of the code that solves the actual problem, like analyzing that medical scan,
Okay.
and the meta agent, the part that proposes and makes modifications, and they combined both of those isolated systems into a single editable program.
Oh, wow. So they merged the student and the teacher into one single file.
Exactly. And crucially, that single file is written in Turing-complete Python.
Wait, before we move on, you said Turing-complete Python. For those of us who aren't software engineers, what does Turing-complete actually mean in this context? Why is that specific detail so crucial?
That is a really important distinction. A system is Turing-complete if it can be used to simulate any computational logic whatsoever.
Okay.
Think of the difference between, say, the keypad on your microwave and a raw computer processor.
Right.
The microwave keypad only lets you input heating times, right? It's a highly restricted, domain-specific tool.
You can't play Doom on a microwave?
Exactly, can't play Doom. But a raw processor can run a web browser, a video game, or a word processor.
Got it.
So by writing the entire hyperagent in Turing-complete Python, the agent isn't restricted to a menu of pre-approved tweaks. It has the theoretical potential to build any computable machine.
Wow.
It can edit any part of its own code, including the meta-level modification procedure itself.
So it can literally edit the part of its brain that decides how to edit its brain.
Exactly. And the researchers coined a specific term for this phenomenon. They call it metacognitive self-modification.
Metacognitive self-modification.
Right. The AI is no longer just improving its performance on a specific task. It is actually improving the underlying machinery by which it generates future improvements.
Okay, I see.
It completely eliminates the need for the task skill and the self-improvement skill to be perfectly aligned.
Because the meta agent can independently get smarter at being a meta agent, regardless of whether the task is writing code or poetry or physics simulations.
You've got it.
Okay, I have to play devil's advocate here for a second, though.
Sure.
If it is constantly rewriting its own brain, specifically the part that controls how it learns, doesn't it just break?
That is the big question.
Like if I tried to rewire my own nervous system while trying to solve a calculus problem, I am pretty sure I would just forget how to breathe and pass out. How does the system not just corrupt its own files and crash the whole server?
Well, the risk of catastrophic failure is very real, which is why the system architecture the researchers designed is so critical.
Okay, how do they solve it?
They took the hyperagent concept and they integrated it back into that evolutionary archive structure we saw in the DGM.
Oh, the VIP lounge.
Right, the VIP lounge. They created what they called DGM-Hyperagents, or DGM-H.
Okay.
And they prevent total systemic collapse using population-based, open-ended exploration.
Meaning they don't just have one single agent that mutates until it accidentally deletes its own operating system.
Exactly. They retain a massive archive of past hyperagents. When it is time to generate the next generation of AI models, the system probabilistically selects the best parents from this historical archive.
Okay.
And the selection is heavily weighted based on two concrete metrics. First, how well the agent actually performed on its assigned tasks.
Makes sense.
And second, the selection is inversely proportional to the number of its children that successfully compiled.
Wait, so it actually checks if the new code compiles before letting it loose?
Yes. By balancing task performance with successful code compilation, the system basically guarantees it won't get trapped in a broken loop where it just writes gibberish Python that crashes the environment.
Right, because if it writes gibberish, it won't compile.
Exactly. If a new variant breaks its own foundational code, it simply fails to compile. It never gets selected to be a parent, and the evolutionary archive just branches off from a healthier, older version instead.
That is so smart. It enforces a steady, stable exploration of new code architectures.
It really is a brilliant safeguard.
Okay, so it survives standard software testing, doesn't break its own code, but, being a functional piece of software is really just the baseline.
Right.
The true test of a self-improving system is whether it can conquer complex domains it wasn't specifically built for.
And to prove that the metacognitive self-modification actually works, they first ran it through a polyglot coding benchmark.
A polyglot benchmark, what does that actually test?
It tests the AI's ability to write functional code across a wide variety of different programming languages. So Python, Java, C++A, and so on.
Okay, to make sure it didn't forget the basics.
Right. The researchers needed to ensure the new architecture didn't lose its core functionality compared to the older models.
And how did it do?
Well, the initial baseline agent scored a 0.140. But the DGM-H system, through its self-guided evolution, improved that score up to a 0.340.
Wow, that's a big jump.
It is. That matched the absolute best established algorithms in the field.
Okay, so it proved the baseline mechanics are sound. But code evaluating code is still somewhat of a closed loop.
Yes.
But they didn't stop there. They pushed this system into subjective tasks.
They did.
Here's where it gets really interesting. They moved into the paper review domain.
Yeah, and the paper review test environment is historically brutal for AI.
I can imagine.
The task is predicting whether actual AI research papers submitted to top-tier machine learning conferences will be accepted or rejected by human peer reviewers.
That is so subjective.
Extremely. There is no single mathematical right answer to whether a research paper is, novel or impactful. It requires deep qualitative judgment.
So I am curious how the older system, like the original DGM with that fixed 1995 teacher, handled this kind of ambiguity.
It failed entirely. The original DGM scored a flat 0.0 on the test tasks.
0. Wow.
Yeah, 0. Without human software engineers stepping in to manually rewrite its instruction generator to understand the nuances of academic peer review, it couldn't adapt at all. It simply didn't know how to improve at a subjective task.
But the new system, though, the DGM-H, with the ability to rewrite its own teacher.
It jumped from that 0.0 up to a 0.710.
That is a staggering leap in capability.
It really is. It even significantly beat a heavily engineered, open-sourced, static baseline system that was designed specifically for this task called the AI Scientist V2.
And what did that score?
That one only scored a 0.630.
That's crazy. And looking at the source text, what really stands out to me is how the AI achieved that score.
Right.
It didn't just tweak its That is incredible. And then the researchers pushed it even further into a simulated physical world. The third testing domain was robotics reward design.
Yeah, they utilized the Genesis physics simulator for this.
Genesis.
Right. It is a fantastic testbed because it requires the agent to interact with complex external environments involving, gravity, momentum, friction.
Real-world physics stuff.
Yes. And the task for the AI wasn't to directly control a simulated quadruped robot.
Yeah.
The task was to write the complex mathematical reward functions that would be used to train that robot via reinforcement learning.
Got it. So the AI is acting as the robot's physical trainer. It has to write the algorithm that dictates what the robot gets rewarded for doing, so the robot eventually learns the desired physical behavior.
Exactly. And there is a specific anecdote from the test logs that perfectly illustrates why open-ended self-modification just crushes handcrafted systems.
Let's hear it.
So the test task was simple. Generate a reward function that maximized the robot's torso height.
Like, just get the robot's body as high off the virtual ground as possible.
Right. And the researchers first tested a manually customized version of the old system DGM custom.
Okay, the one with the fixed teacher.
Yes. And it made some initial progress, but it quickly got stuck in a local optimum.
What did it do?
Well, it figured out how to write a reward function that told the robot to lock its joints and stand straight up on its legs.
Okay.
So it achieved a standing posture, and then it completely flatlined. It couldn't figure out how to improve beyond simply standing tall.
Because its fixed meta agent couldn't conceptualize a fundamentally different approach to the physics problem.
Exactly.
And for anyone unfamiliar with the term local optimum, it's like trying to win a jumping contest by just stretching your neck as high as you possibly can.
That's a great way to put it.
You know, you've technically maximized your height in that specific posture, but because you never thought to, say, bend your knees, you will never actually leave the ground.
Right.
So the old AI was stuck stretching its neck.
Yes, but the DGM-H, the hyperagent, experienced a totally different trajectory.
Because it could edit its own brain.
Right. Because it could modify its own search strategy and literally rewrite its approach after observing failures, it successfully generated a task agent that figured out a completely novel physical strategy.
What did it do?
It wrote a reward function that taught the robot how to crouch, build momentum, and jump.
It figured out jumping.
It did.
It didn't just optimize the standing posture. It rewrote its approach to discover a completely novel physical behavior that the human programmers never explicitly prompted.
It's pretty amazing. So we have observed it master subjective academic paper reviews, and we have observed it master simulated physics,
Right.
which brings us to what the source paper treats as the ultimate holy grail of artificial intelligence.
Okay, what's that?
Transferring the skill of learning itself.
Okay, so like, if you spend a year learning how to study effectively for your history classes, taking meticulous notes, building study guides, creating a schedule, does that meta skill make you better at studying for a calculus class? Even if you know absolutely nothing about calculus,
Yeah.
does the ability to learn carry over across disciplines?
Exactly. And to test that exact premise, the researchers established a rigorous meta-evaluation.
How did they test it?
They utilized Olympiad-level math grading from the IMO grading bench.
Oh, wow. Okay.
Yeah, in this environment, the agent is given an international mathematical Olympiad problem, a complex candidate solution submitted by a student, the official grading guidelines, and reference solutions.
That's a lot of data.
It is, and the AI has to analyze the logic and predict a discrete score.
So a highly complex, rigorous, multi-step logic task.
Very much so. And here's the truly fascinating part of the experiment design.
Okay.
The researchers took the specific hyperagents that had been continuously optimized purely in the paper review domain,
Okay.
along with the hyperagents optimized purely in the robotics domain.
The ones that figured out jumping.
Right. And they took these agents and suddenly dropped them into this entirely new math grading domain.
Wait, so these agents had never seen a mathematical Olympiad problem before in their entire evolutionary life cycle.
Never.
But their internal teachers, their meta-agents, had spent dozens of generations learning how to improve their own systems for reviewing papers and training robots.
Exactly. And the results showed that the meta-level improvements transferred completely.
Really?
Yes. The hyperagents that had learned how to self-improve in robotics and paper reviewing were significantly faster and more effective at generating highly accurate math grading agents than a system starting from scratch.
So the AI had actually learned universal strategies for self-improvement that transcended the specific tasks it was trained on.
It did, and the researchers were actually able to isolate the specific code artifacts the AI invented for itself to achieve this transfer.
Wait, it invented code artifacts?
Yes. During its long evolution in those earlier domains, the meta-agent realized it was losing valuable data between generations.
Like it was forgetting things.
Right. So it learned to build persistent memory into its own architecture.
You're kidding.
No, it independently coded its own Python class, literally naming it Performance Tracker, to monitor its historical progress and performance metrics across different evolutionary generations.
Okay, just think about what that implies for a second.
I know.
The AI isn't just memorizing flashcards to pass a test. It looked at its own failures, realized it was forgetting things from past generations, and independently invented the concept of a study journal to fix its own cognitive flaw.
Exactly.
It wrote the software to build that journal, and then it took that journal with it when it was ripped out of the robotics lab and dropped into the math competition.
It is the purest algorithmic definition of metacognition. It is thinking about thinking.
Wow.
Because the agent is written in editable Turing-complete Python, it possesses the capability to implement any cognitive tool or data structure it dreams up to aid its own learning process.
That is just...
And the self-improvements learned in one run compound, accelerating learning in all subsequent runs, completely regardless of the subject matter.
Honestly, my brain is slightly on fire right now in the best way possible.
It is a lot to take in.
It really is. When you look at an AI that can write its own code, build its own persistent memory architecture, and literally compound its own intelligence. I mean, it does make you pause.
Oh, absolutely. And the researchers are acutely aware of the implications here. The safety protocols outlined in the paper are extensive.
Good, because that sounds necessary.
Very. When you are dealing with editable programs that can theoretically write any computable machine, you are dealing with immense foundational power.
Right, so we aren't hooking hyperagents up to the actual power grid or the financial markets just yet.
Definitely not. All of the experiments detailed in the research were strictly sandboxed.
Okay.
They operated in heavily isolated virtual environments where the code could not execute commands affecting external systems or the broader internet.
Which makes total sense.
Furthermore, the evolutionary runs required strict human oversight. The paper emphasizes that as these systems become more capable of open-ended autonomous improvement, our human frameworks for containment, alignment, and monitoring have to evolve just as quickly to keep pace.
Because the potential for unbounded improvement is no longer just theoretical.
Right, and it demands rigorous responsibility.
So what does this all mean?
That's a big question.
If we zoom out from the Python classes, the simulated jumping robots, and the math Olympiads, we're really catching a glimpse of a very specific future.
We are.
Because for our entire history, technological progress has been bottlenecked by human biological limits. You know, how fast we can type on a keyboard, how fast we can run physical experiments, how fast our neurons can process new information.
Right.
But this research on hyperagents shows us that the progress of AI is actively shifting from a human-paced bottleneck to an autonomously accelerating process.
The machine is figuring out how to build a better machine entirely on its own.
Yeah. We talked at the beginning of this deep dive about that hypothetical hammer forging itself a better handle overnight.
Right.
If an AI can perfectly optimize its own ability to learn, if it can invent its own memory structures, track its own performance over time, and completely rewrite its own cognitive processes from scratch, what happens when it realizes that the biggest bottleneck to its continued evolution is the speed at which humans can evaluate it?
It is a profound question regarding our place in the loop.
At what point does the tool decide that the hand holding it is moving too slow? Thanks for listening, everyone. We'll see you on the next deep dive.